Hello and welcome to the second part of the thermal energy storage lecture. In this lecture we will talk about latent heat storage, and the big advantage of latent heat storage is that we can realize storages that have almost no thermal losses. And that is a very big advantage because then I don't need anymore here this hot coat here in the video studio. So the latent heat storage, when we see here this diagram, there we see on the horizontal axis the temperature, and on the vertical we see the stored heat. And when we then see the blue line, the one for a sensible heat storage, we see that with every additional heat the temperature will be increased. And that is different when we go for a latent heat energy storage. There, at a certain temperature, we add energy, but the temperature does not rise anymore because the material will perform a change in phase. And that is also the reason why those materials are called PCM, a phase change material. That means we can store in this phase change a quite high amount of heat without that the temperature increases anymore, and therefore also the losses might be decreased a lot. So for example, we have a phase change from solid to liquid. Theoretically we also could have from liquid to vapor, but that is quite often comes along with a high change in volume, so quite often we use more the solid to liquid phase change. An example for that are these heat cushions that we see here. So here we have water fixed in a crystal structure of salt. Its durability depends on constant water concentration within that mixture, and anorganic materials, they can speed up the crystallization process in order to release the heat. High volumetric energy storage density and good heat capacity can be realized by those latent heat energy stores. One possibility to realize a latent heat energy storage is, for example, with the help of paraffins and composite materials. Paraffins are organic mixtures made of saturated hydrocarbons produced by distilling crude oil. They have a congruent melting and high cycle stability. Their disadvantage, and what makes it quite complex to realize technically latent heat storage, is that they have a very low thermal heat conductivity. So it's quite difficult to get the heat into the storage and also to discharge the storage again. Increasing heat conductivity therefore is done with metal and plastic composites. Here we see an example of a macro encapsulation where we have a material where a PCM is implemented which has a diameter of almost a centimeter or even bigger. And then on the other hand we have the micro encapsulation where we add small particles of these PCM materials into building structures, for example, in order to have a better thermal behavior of the building in the summertime. But now, in order to increase the heat transfer of those systems, many technical solutions have been developed and still under investigation. The first is just have a simple storage systems without and with internal heat conducting structures that we see here on the left without, and the two on the right have internal structures that just have the task to better get the heat to the PCM materials. And then we have those module storage systems on the left side, those plate modules where the heat fluid is going around those plates. And on the right side we have the ball modules where again the liquid, the heat fluid passes around those balls in order to transfer the heat. Then we have storages that have implemented an internal heat exchanger to get better the heat into the storage and out of the storage. And on the right side we have an active indirect storage system with an internal agitator that should mix the material and therefore get a better heat conductivity. And finally we have so-called slurries two different variants. On the left, the direct contact storage system, and on the right side, the slurry storage system. Here we have an overview about many latent heat energy storage systems. And there again we see on the horizontal we have the melting temperatures of those materials. And there we see we have it from minus 100 degrees Celsius up to several hundred degrees Celsius. And then on the vertical we have the melting energy in kilojoule per liter. And then we see typical for colder temperatures, for cold storage, we use water ice systems. In the building sector, where we talk about temperatures that we need between 20, 30, 40 degrees melting temperature, quite often we have those in green marked paraffins. And then it changes until to the right, when we have then those chlorides, carbonates and fluorides, where we can realize melting points of several hundred degrees Celsius and also with a quite high melting enthalpy. Also here we will end up with a small video explaining again the principle of latent heat storage systems. Hi, how does a latent heat energy storage work? Here the thermocushion Hugo will help us. Hugo is a latent heat energy storage device. At the beginning, Hugo is in a charged state. Hugo's interior is composed of a liquid salt hydrate. Even when Hugo is charged, his temperature is the same as the ambient temperature. But when it is cold outside, Hugo should help us to keep our fingers warm. How does that work? Within the salt solution, they have a metal plate. When this is folded, a process is started that is called crystallization. Small cracks in the surface of the plate deliver crystallization seeds where ions are formed. Within seconds, an avalanche of crystallization start forming grid structure. This rapid change of its phase with constant ambient temperature releases an enormous heat with which our hands can be heated. This is called latent heat or hidden heat. Because the heat is only released with a change of the phase, for example from liquid to solid. This phase change occurs automatically, for example when ice melts at a temperature of 0 degrees and melting enthalpy is set free. The second possibility is that the process is started via a foreign material, as it is the case with Hugo. Temperature reached almost immediately its maximum and keeps almost constant, whereas the energy content decreases permanently. The process stops when the salt hydrate is completely solid. To recharge the latent heat energy storage, the salt hydrate needs to be liquefied again. This is done by delivering heat energy. The cushion is given into a pot with hot water. What are the specifics of latent heat energy storage? The extraordinary is how the heat is generated. As it is necessary to have a phase change start, the process of discharging the heat energy can be stored for a long time without losses. In contrary, with sensible heat energy storage, that means a charged storage always comes along with a high temperature. With high temperature differences towards the ambient temperature, this heat energy storage type tends towards high losses. That is the advantage of the latent heat energy storage. It can keep its capacity of a long time. In research, media are investigated that have a high melting enthalpy with a required melting temperature level. A focus lies on building heating and cooling. Further developments tend to reach higher charging and discharging powers. So in the next video we'll continue with thermochemical energy storages. Thank you very much.